This is a video from section 4.3. The directions say to find the intervals on which f is increasing or decreasing and find the local maximum and minimum values of f. So let's take a look at example 1. Suppose f of x equals x cubed minus 6x squared minus 35x. And one thing I'd like to note is the domain of the function is from negative infinity to infinity. So I just got to put an open interval around infinity. Step 1 is to find the derivative. And so the derivative is 3x squared minus 12x minus 135. We're going to set f prime of x, the derivative, equal to 0 and solve for x. So in other words, we're going to find the critical numbers of f. So by doing so, we set 3x squared minus 12x minus 135 equal to 0. Factor out a 3, we get x squared minus 4x minus 45 equals 0. We factor, we get 3 times x minus 9 times x plus 5 is equal to 0. Solving for x, we get x equal 9 or x equal negative 5. And so our critical numbers are negative 5 and 9. Okay, and so what I'm going to do, and let's erase that negative 6 for a minute. I'll explain that shortly. So we have a number line, and we're going to break up that real number line utilizing the critical numbers. So notice how I have a negative 5 and a 9. So we're going to break this number line up into 3 intervals utilizing those critical numbers. Okay? So if you notice, our first interval is from negative infinity to negative 5. So notice I go from negative infinity up to the first one, critical number. Then I go from negative 5 to 9 for my second interval, and from 9 out to infinity. And so if you notice, we have 3 intervals. So negative infinity to negative 5, negative 5 to 9, and 9 to infinity. And so what I'm going to do is I'm going to test a point inside each of those intervals. And you can't test critical values. So that's the condition. And so when I look to the left of negative 5, I'm going to test x equal negative 6. When I look in between negative 5 and 9, I'm going to test x equals 0. 0 is a really nice number. And when I look to the right of 9, I'm going to test x equal 10. And what I'm going to do is I'm going to plug it into the first derivative. So if you notice, I test x equal negative 6, x equals 0, and x equal 10. So if you plug it in, if you plug those test points into the first derivative, what you're going to notice is f prime of negative 6 is positive. And what that says is f is increasing on the interval from negative infinity to negative 5. When I plug x equals 0 in the first derivative, you're going to find that it's negative. So, and by the way, the reminder is down here. This is what the function is. So when I replace x with 0, notice how f prime of 0 is negative 135. And that is absolutely negative. It doesn't matter what the number is. You need to know what the sign is. So when the first derivative is negative, what that on this interval, what that tells me is that f is decreasing on the interval from negative 5 to 9. And when I plug x equal 10 in the first derivative, you're going to find that it's positive. And by the way, don't get sucked in. You want to make sure to test those points because it's not going to always alternate. We can come up with an easy counterexample to that. So here, f is increasing on the interval from 9 to infinity. When you plug in 10, f prime of 10 is positive, so it's increasing. And so what that tells me, now, think pictorially. And I'm going to come back to the number line. Here, we'll come over here for a sec. Oh, let's go back. Here we have a number line, and here's negative 5. When you go from increasing up to -5, and then you start decreasing. Notice how I'm on top of the mountain. And so what that tells me is f has a local maximum at f of -5, which is 400. So by the way, I'm plugging -5 back into the original function. When you go from decreasing, and by the way, here's 9. So let me erase real quick. When you go from decreasing down to 9 to increasing, you're at the bottom of the heap. And that's going to produce a local minimum. So increasing to decreasing, maximum. I literally think like a picture. Decreasing to increasing, minimum. And so f has a local maximum at f of -5 equals 400, and a local minimum at f of 9 equals -972. So I just plugged those critical numbers into the original function. Let's look at example 2. So f of x equals x squared minus 24 over x minus 5. When you take the first derivative, I apply the quotient rule, and you're going to see that the first derivative is of x. Let me say it this way. You're going to see that f prime of x is x minus 4 times x minus 6 over x minus 5 squared. So we need to find the critical numbers. Okay? Once you take the derivative, that's here, right? Ultimately, we need to find critical numbers. Set f prime of x equal to 0. And then x minus 4 times x minus 6 is equal to 0. X is 4 or x is 6. So the critical numbers are 4 and 6. Now, you might ask, why didn't I set x equal 5 to be a critical number? The reason why is because 5 is undefined. It's not part of the domain. And so x equal 5 is not a critical number. That's tricky. And I have an example that addresses that. Okay, so yes, f prime of x is undefined at x equal 5, but because x equal 5 is not part of the domain of the function, it's not a critical number. And so we're going to go through and we're going to break up the number line. Yes, I'm including 5 because it is undefined at 5, right? And so we have these intervals, negative infinity up to 4, 4 to 5, 5 to 6, 6 to infinity. So if you notice, we have 4 different intervals this time. And I'm going to test a point. So I'll test x equals 0, x equal 4.5. I just went for the middle. Now, could you test x equal 4.1? Absolutely. It works. As long as it lies inside the interval from 4 to 5, you are safe. I tested x equal 5.5, and then I just plugged in 7. And what you're going to find is that f prime of 0 is positive, f prime of 4.5 is negative, f prime of 5.5 is negative, and f prime of 7 is positive. And so when the derivative is positive, you're increasing on the interval negative infinity to 4. Since the derivative is negative at x equal 4.5, the function is decreasing. DEC is for decreasing on the interval 4 to 5. And if f prime of 5.5 is negative, you're decreasing on 5 to 6. And f prime of 7 is positive, you're increasing on the interval from 6 to infinity. Next page. So f has a local max at f of 4 equals 8. Why? Because you're going from increasing to decreasing at x equal 4. And then over here, you're going from decreasing to increasing. And the breakpoint is 6. So you're going from decreasing to increasing. So you're at the bottom. So f has a local max at f of 4 equals 8, and f has a local minimum at f of 6 equals 12. And I literally think about the graph increasing to decreasing, maximum, decreasing to increasing, minimum. I'm literally drawing that. Example 3, f of x equals x to the 2/3 times x minus 3. And by the way, the domain for example 3, interestingly, is negative infinity to infinity. Okay? So when we take the derivative, we get 5x to the 2/3 over 3 minus 2x over x to the 1/3. If I get a common denominator, the LCD here is 3x to the 1/3. Now, so it turns out f prime of x is 5x minus 6 over 3x to the 1/3. Now you have to address where f prime of x is undefined. Why? Because at x equals 0 is part of the domain of the function. Okay? So it's legal. So that is a critical value. So f prime of x is 0 when x equals 6/5. So basically I set the denominator equal to 0 and solve for x. And f prime of x is undefined when x is 0. And so here's my number line, and I broke up the number line utilizing those critical numbers. So we have 0 and 6/5. And that's going to produce some intervals. In fact, we're going to have 3 intervals. And so notice we go from negative infinity to 0. Remember, 0's my first critical number. And then from 0 to 6/5 and 6/5 to infinity. And same game, we're going to test points. X equal -1, x equal 1, and x equal 2. Okay? And I'm plugging those test points into the first derivative. So f prime of -1 is positive, and what that tells me is that the function is increasing on negative infinity to 0. I plug 1 into the first derivative, and I find that f prime of 1 is negative, and so the function is decreasing on the interval from 0 to 6/5. And when I plug x equal 2 in the first derivative, I get f prime of 2 is positive, and so f is increasing on the interval from 6/5 to infinity. And so f has a local max. Remember, when you go from increasing to decreasing, you've got a max. So f has a local maximum at f of 0 equals 0. And when you go from decreasing to increasing, remember the breakpoint is at 6/5. And so f has a local minimum at f of 6/5, which ended up being approximately negative 2.03. Okay? I hope this is making sense. And we got one more example here. F of x equals x to the 4th e to the negative x. This is example 4. F prime of x ended up being x cubed times 4 minus x over e to the x. E to the x is never 0. Okay? Now, f prime of x is 0 when x is 0 or x is 4. Okay? So, again, I break up the number line into 3 different intervals where the intervals come from my critical numbers, right? So I'm utilizing those critical numbers to get my intervals. So if you notice, the same pattern, I'm going to go from negative infinity to 0, 0 to 4, and 4 to infinity. And I'm going to test a point inside each interval. X equal -1, x equal 1, and x equal 5. I try to keep them nice, small numbers. Could I have tested x equal -100? Absolutely. It's just an inconvenient number. So I come over here. F prime of -1 is negative. So I'm plugging, so again, let's make sure we understand. I'm plugging those test points in the first derivative. And since f prime of -1 is negative, what that tells me is f is decreasing on the interval from -infinity to 0. And when I plug x equal 1 in the first derivative, f prime of 1 is positive, and so f is increasing on the interval 0 to 4. And when I plug in x equal 5, f prime of 5 is negative, and so f is decreasing on the interval from 5 to infinity. And so f has a local minimum, right? Because you're going from decreasing to increasing, right? So f has a local minimum at f of 0 equals 0. And if you go from increasing to decreasing, that's going to produce a maximum. So f has a local maximum at f of 4 equals 256 e to the -4. Okay, and that'll conclude this video for section, this is 4.3. And so what we did is we did 4 examples on finding intervals for which f is increasing or decreasing and figuring out what the local maximum and minimum values of the function are. Okay, thank you.